Welcome to my talk titled Learning Travelling Salesman Problem Requires Rethinking Generalization. TSP is probably the most extensively studied NP-hard problem and has really served as an engine of discovery in applied mathematics for years now. Today, deep learning is being used to tackle TSP and combinatorial problems, and it's also becoming a benchmark to advance deep learning. This talk is really about deep learning approaches for combinatorial optimization problems, with TSP being used as a benchmark. And our main finding is that a lot of the approaches today can be used to solve trivially small problem instances, but extrapolating to larger and more realistic instances is still an open problem and an exciting research question. Something inspiring this work is this paper, Understanding Deep Learning Requires Rethinking Generalization. And this award-winning work really introduced this idea that deep neural networks can memorize lots of complex random data, but probably what the community should be caring more about is their generalization property, their extrapolation capability. And we want to bring the same perspective to deep learning for combinatorial optimization. So what motivates neural combinatorial optimization is this idea of non-learned, cheap, approximate solutions or heuristics without much theoretical guarantees. And they're hand engineered, they're handcrafted, but super fast. Now, with deep learning, we don't like handcrafting. So learned heuristics for TSP and generally for any combinatorial problem will try to learn to go beyond human intuition by just studying problem instances and constructing these heuristics based on data. And there have been many recent works which are showing the possibility of doing this for trivially small TSP. So many of these papers have been published at top conferences, and my own bachelor's thesis was also on this topic. And I believe that these are really proofs of concept. These are evaluated on fixed TSP sizes. So we really, set a benchmark. We say that we train and test on TSP of 50 or 100 cities, and then we measure the average tour length. And what we want to do is we want to constantly improve over the non-learned insertion heuristic. And what we've seen over the years is that these models are kind of getting better and better. Every year with every publication, we get better architectures for TSP. And in fact, we are now very, very close to Concord. And this is promising, right? Like this really leads to this question that can we now take these ideas, this learning driven combinatorial solvers to the real world, to maybe larger scale TSP or larger scale problems which we haven't studied before. So the research question that motivated our work is that how do we scale to practical sizes? Do these approaches actually scale to practical sizes? So option one obviously is to just scale and see what happens, right? Just train these models on big sizes and see what happens. And we found that this is really challenging. So here I'm showing you two graphs. On the y-axis is the optimality gap or the closeness to the Concord solver, which is an exact TSP solver. This is the optimality gap on TSP 200, so instances of size 200. And on the x-axis are firstly the sample complexity of any learning method and then the wall clock time. The line in brown, which is at around say 10% optimality gap, is the insertion heuristic, the non-learned heuristic. And we ideally want any learning-based method to be a lot better than this heuristic, right? But here, the blue curve is what we see when we train on TSP 200 from scratch. What we found is that this is really difficult for university scale hardware to train on TSP 200. We were essentially unable to outperform the insertion heuristic, even if we train with over 10 million TSP 200 samples. for over 500 hours at on university scale hardware. Obviously, you can see these curves will keep getting better with more training, possibly parallelizing the training process, possibly huge models, at the scale of industrial research labs. Um, but but you can see that these approaches are not the most scalable yet, right? Like it seems like it's difficult to get huge benefits from scaling them. So option 2 that we are interested in is transfer learning from small instances to something very large. So here this green curve is transfer learning from very small trivial TSP 200, TSP 20 and TSP 50. So in this size range, it's very cheap to train, right? And what you can see is the wall clock time is much, much lower. Um, whereas the performance when you train on these small sizes but transfer to TSP 200 is already better than training on TSP 200 from scratch. Essentially, what this means is that even on these trivially small problem instances, the models are able to learn at least something useful that is able to extrapolate somewhat to TSP 200, right? And this is promising. This means that, if we're able to bring this green curve down, if we're able to, improve the performance of these models more on these small instances, we can really further improve extrapolation on very large problems and potentially tackle real world realistic instances. We ask this question, so which architectures, learning paradigms, and inductive biases are actually enabling strong zero-shot generalization to larger TSP instances? We already know that any of these new architectures, new models of the past few years will perform really well on fixed sizes, but we haven't really studied how they generalize. To investigate out of distribution generalization, the first step that we took was to unify all these new architectural ideas into one single pipeline, into this 5-stage pipeline, which we could then, experimentally compare and tweak each component of this pipeline to really test which components lead to real strong generalization. So specifically, this pipeline consists of, defining TSP as a graph problem, maybe as a full graph or a k-nearest neighbor graph. Um, so each city in this graph is then converted into a hidden representation or feature in deep learning. So this is usually done by a graph neural network or a transformer or any other embedding approach. Once we have these embeddings, the next step is to really convert them into probabilistic decisions or solutions. So in the case of TSP, we want to say which edges belong to the solution, right? So in this case, we can either make independent decisions on each edge, just go from the feature vectors to some sort of probability that this belongs or doesn't belong to the tour. Or what we can do is we can also do the same thing in a step-by-step fashion. So we can arbitrarily say that I'll start here and then decode my solution one by one. So I'll move from one city to the other, and ultimately what I'll arrive at is this sort of probabilistic heat map or soft solution. And this whole part is learned end to end. Finally, what we need to do is we need to then apply a classical graph search or graph traversal algorithm on this probabilistic solution, which will give us a discrete solution. This is our final solution, which has been given to us by our neural network solver. The final part is to learn the neural network solver, obviously, and this can be done either via supervised learning, where we are really learning to imitate the solutions from something like Concord. So we know Concord is close to optimal, so we'll imitate what Concord has solved. Or we can even use reinforcement learning. So here we can, define some sort of cost function, which we can then minimize using RL. Now, the second part or the second step is once we have this pipeline, as I said, we want to probe this pipeline in a fair and controlled manner. So we design experiments to give us performance in such charts. Um, so what we have in this charts, firstly, is that we are able to compare various models fairly under the same experimental setting in terms of number of parameters and training computation. Secondly, we aren't measuring performance just on a fixed size. So maybe each model is trained on a range of sizes, but we will measure its performance across various different TSP sizes up till TSP 200. And really the goal is to see how they generalize, right? So to characterize this generalization, we also will always plot the insertion heuristic. Here, the insertion heuristic is really being used to quantify what good generalization means. And ideally, you want your learning-based method to always generalize better than this insertion heuristic, although we saw that it doesn't do so at larger TSP. On the y-axis is always the optimality gap to the Concord solver. And this gap is measured as the average over a few thousand instances. So with this fair experimental setup in mind, we probed the pipeline and we really try to find out like which architectural decisions are leading to better generalization, right? So what we found was firstly that using sparse graphs, which are defined smartly, is really useful to extrapolate. So if you, for example, maintain a consistent graph diameter across TSP sizes, then the learning-based methods can generalize far better. Interestingly, when it comes to the embedding function, the more expressive models like GAT, graph attention, and GNNs which use sum are not so good at generalization. And in fact, models which are agnostic to changes in node degree, so something like max aggregation or mean aggregation, are significantly better at generalization. In terms of performance, it's worth noting that all these models are about the same, like they're equally good at performance within the training size range. But when it comes to generalization, it becomes obvious that these decisions about how you build your GNN actually significantly impacts its generalization capacity. Now, crucially, something even more important to generalization is how you decode. So TSP is a sequential problem, right? And we found that it's really important to build in the sequential nature into your model as well. So if you decode autoregressively or step by step, then you obtain significantly stronger generalization than if you were to decode in a single shot. The single shot decoding approach might be faster, but its generalization performance is much, much worse. Finally, it's also worth noting this interesting relationship which we found between how you learn and how you search for solutions. So if you're doing RL, right, then you're really good at greedy decoding, but supervised learning models somehow seem more amenable to beam search, more amenable to probabilistically searching the solution space that they create. And this obviously is not conclusive because supervised learning, while being better within the controlled setup, may not scale that well, right? With supervised learning, we obviously always need labeled data, but with reinforcement learning, we do not need to always create labels, so we can simply keep scaling data in RL without as much cost. So there's an important interplay between these two approaches as well. Ultimately, though, what we saw is that we're still far away, from the insertion heuristic. We're still not able to beat insertion heuristics at TSP 200. This is not just in my work, but like I've been monitoring other work in this area, and what I've seen is like even for other papers, it's really difficult for these models to extrapolate to larger sizes. We just haven't seen architectures which are specially designed for this extrapolation. Now, the goal of this talk was to really motivate us to do so. And for me, I think it's exciting how we will close the gap to learned heuristics and then hopefully to Concord on TSP and in other real world NP hard problems as well. I'm excited about, for example, more expressive graph neural network architectures, which are specifically designed to be scale invariant. I am excited about how they will combine with classical search techniques like Monte Carlo tree search and potentially, more sophisticated post hoc local search techniques. And finally, it's also exciting to think about this extrapolation problem as a meta-learning problem, right? Like, how do we learn parameters for a model that are going to be useful to extrapolate to the same problem, but at a larger scale? So the underlying rules are the same, the underlying constraints are the same, but we want to go to a larger instance of the problem. And I'm looking forward to progress in this area. And by the way, the preprint is online, the code is on GitHub, and I encourage you to check out a blog post that I've also written about this topic. Thank you for listening, and I'm happy to take questions.